Hi everyone, welcome to my YouTube channel Erudispace. I am Dr. Mohanty and today we will discuss about the dual cycle. So in dual cycle, first I will tell you how the dual cycle is similar and different to both Otto cycle and diesel cycle. Then I will draw the PV and TS diagram of the dual cycle, and then I will derive an expression for the air standard efficiency of the dual cycle in terms of temperatures at cardinal points, and then I will discuss the expression for efficiency of the dual cycle in terms of different ratios. So first, what is a dual cycle and what are the processes? Let me draw the dual cycle in PV and TS diagram. So you can see that there are 5 processes. The processes are 1, 2, 2, 3, 3, 4, 4, 5 and 5, 1. 1, 2 is actually reversible adiabatic compression process or isentropic compression process. So this is isentropic compression process. 2, 3 is your constant volume heat addition process. Three, 4 is constant pressure heat addition process. 4, 5 is reversible adiabatic expansion or isentropic expansion process. And 5, 1 is constant volume heat rejection process. So, unlike the Otto cycle and diesel cycle, here you are having 5 thermodynamic processes taking place. Out of that, the process 1, 2 is your isentropic compression process, that is same as the Otto as well as the diesel cycle. You do have an isentropic expansion process which is also happening in both the Otto as well as diesel cycle. You have a constant volume heat rejection process which is also happening in case of your Otto and diesel cycle. So 3 of the processes are exactly same as the Otto cycle and diesel cycle, but here the heat addition is taking place both at constant volume as well as constant pressure. In case of an Otto cycle, the heat addition takes place at constant volume, whereas in case of a diesel cycle, the heat addition takes place at constant pressure. So here, if you consider the heat addition or heat supplied to be QS, QS is actually the summation of Q23 plus Q34. So this is your QS. Then this represents your heat rejection. That is a constant volume heat rejection process as has been happening in case of your Otto cycle and your diesel cycle. And this is the work done upon the system during isentropic compression and this is the work obtained from the system during isentropic expansion. Now, we can derive an expression for the efficiency of the dual cycle in terms of temperatures at cardinal points. All of us know that efficiency is 1 minus heat rejected divided by heat supplied. So in this case, the heat rejected is during process 5.1 and this is mCV into temperature difference, that is T5 minus T1 divided by the heat supplied. I have already told you that the heat supply is taking place first at constant volume followed by at constant pressure. So this is mCV into T3 minus T2, that is the heat addition taking place in process 2-3, and then the heat addition taking place during process 3-4 where it is taking place at constant pressure. So it is mCp into temperature difference, that is T4 minus T3. So this can also be represented as 1 minus, if you divide both the numerator and denominator by Cv, you get it as T5 minus T1 divided by T3 minus T2 plus gamma into T4 minus T3. Because all of us know that the ratio between Cp and Cv is your adiabatic index, that is your gamma. One thing that you should remember, that contrary to the general perception that the dual cycle has a limited application, the dual cycle actually approximates the compression ignition engine, because the heat addition is due to compression and the fuel is actually injected before the compression process is over. So in actual compression ignition engine, some person will be constant volume heat addition followed by constant pressure heat addition. That's why this is also known as your semi-diesel cycle. We also call it limited cycle, and dual cycle obviously is the name with which we are all well acquainted with. So let this be equation 1, and this actually represents the expression for the air standard efficiency of the dual cycle in terms of temperature parameters at cardinal points. So now we will actually derive an expression for the air standard efficiency of the dual cycle in terms of different ratios. Here we will consider 4 ratios, and these ratios are your compression ratio, your expansion ratio, your cutoff ratio, and your constant volume pressure ratio. First, you are having the compression ratio denoted by Rk, and that is V1 by V2. V1 is the volume before the compression process starts, and 2 is where the compression ends. So the ratio between V1 and V2 is what we call your compression ratio, Rk. Then you have an expansion ratio, Re. Expansion is starting at 0.4 and is ending at 0.5, and this ratio is V5 by V4. Then you have the cutoff ratio. The fuel is actually added at 0.3 and the process ends at 0.4, and the cutoff ratio Rc is equal to V4 by V3. Then the last one is constant volume pressure ratio. Constant volume pressure ratio denoted by R suffix P is the ratio of the pressure at point 3 to the pressure at point 2. This is P3 by P2. Now first we will establish the relationship between the three ratios RA, RE and RC. All of us know that RK is V1 by V2. V1 is same as your V5 because this is a constant volume process. So you can substitute V1 by V5 and V2 is same as your V3. You can substitute V2 by V3. Now you can multiply it by V4 and you can divide it by V4. As a result, the value of the ratio will remain unchanged. You can represent this as V5 by V4 multiplied by V4 by V3. So this is equal to your V5 by V4 is your RE and V4 by V3 is your RC. You denote this as equation 2. Now, to express the efficiency in terms of different ratios, four of the temperatures are to be represented in form of another temperature, and it is observed that if the temperatures are represented in terms of T4, then the simplification of the expression is the easiest. So we will convert all the temperatures in terms of T4. So first, RC, you know, that is equal to V4 by V3, and 3-4 is a constant pressure process. For a constant pressure process, the ratio between the volumes is equal to the ratio between the temperatures. Now, this implies T3 is equal to T4 by RC. Let this be equation 3. Now, for process 2-3, it is a constant volume process. So for constant volume process, the combined gas equation PV by T is equal to constant reduces to P by T is equal to constant. So from this you get T2 is equal to P2 by P3 into T3. That is equal to T3 divided by RT. And we know that T3 is T4 by RC. So this implies T2 is equal to T4 by RC into RT. So what we have done, we have simply substituted T3 by T4 by RC. So T2 is now expressed in terms of T4. Let this be equation 4. For isentropic compression process 1, 2, T1 by T2 is equal to V2 by V1 to the power gamma minus 1. This implies T1 is equal to T2 multiplied by, this is V2 by V1. We know that V1 by V2 is Rk. So you can represent this as T2 divided by Rk to the power gamma minus 1. And what is T2? T2 is equal to T4 divided by Rc into Rp. So we can substitute that. So it becomes T4 divided by Rk to the power gamma minus 1 Rc into Rp. This becomes equation 5. And then we'll consider the isentropic expansion process for 5. According to that, T5 by T4 is equal to V4 by V5 to the power gamma minus 1, and this implies T5 is equal to T4, and V4 by V5 is reciprocal of V5 by V4. So you can represent this as 1 upon Re to the power gamma minus 1. And what is Re? From this we know that Re is equal to Rk divided by Rc. So that can be substituted. Instead of Re, you represent this as Rk by Rc to the power gamma minus 1, that is equal to T4 into Rc to the power gamma minus 1 divided by Rk to the power gamma minus 1. This becomes equation 6. So now we'll actually substitute the values of T1, T2, T3, T5 in this equation 1 to find an expression for air standard efficiency in terms of different ratios. So let me substitute the values. Now the efficiency eta is equal to 1 minus, first we have to substitute T5, this is T4 into Rc to the power gamma minus 1 by Rk to the power gamma minus 1 minus T1. T1 is T4 divided by Rk to the power gamma minus 1 Rc into Rp. T4 divided by Rk to the power gamma minus 1 into Rc into Rp divided by, we have to substitute T3 by T4 by RC minus T2 as T4 divided by RC into RP plus gamma into, we'll keep T4 as it is, and T3 H T4 by RC. Now, the T4 can be eliminated from all these expressions because T4 is present both in the numerator and denominator. Now, eta is equal to 1 minus RC to the power gamma minus 1 by RK to the power gamma minus 1 minus 1 by RK to the power gamma minus 1 RC into RP divided by, this is 1 by RC minus 1 by RC into RP plus gamma multiplied by 1 minus 1 by RC. So now eta is equal to 1 minus, we can take 1 by RK to the power gamma minus 1 as common. Then you can take RC into RP as LCM. So this becomes RC to the power gamma into RP minus 1 divided by, you can take RC into RP as LCM. So you get this as RP minus 1 plus gamma times RP into RC minus 1. Now this RC into RP will cancel out this RC into RP, and ultimately you get eta as 1 minus 1 by RK to the power gamma minus 1 multiplied by RC to the power gamma into RP minus 1 divided by RP minus 1 plus gamma into RP into RC minus 1. This you can denote as equation 7. So this is all about the efficiency of the dual cycle in terms of compression ratio, cut-off ratio and constant volume pressure ratio. Already we have derived the expression for efficiency in terms of temperatures at cardinal points. So I sincerely believe that this lecture on dual cycle would be extremely useful for all of you, because we have discussed in detail all the thermodynamic processes, how it is similar and different to Otto cycle and diesel cycle, and of course we have derived the expression for thermal efficiency in terms of temperature parameters at cardinal points as well as these ratios. If you have any doubt related to this, please do put questions so that I will try to answer. Hope to see you soon for another lecture on my YouTube channel Erudispace.